All right, so my plan now is I want to do more Morse homology. I want to do Morse homology, which was alluded to in Mike Usher's talk. I have your lists of sort of things that you thought I was too sloppy about that you'd like to see me give better presentations of at some point, or just things you want to know more about. And I plan on getting around, sort of spending some time to cleaning up that stuff after we've sort of settled on Morse homology and cohomology. And I want to try to talk about quantum duality in that. So, but this won't take that long. There are lots of interesting questions about how you relate Morse homology and cohomology and all the standard stuff from algebraic topology in this setting. The one thing I think I really should do, I guess, I was originally just going to bypass it, is actually show that Morse homology is the same as ordinary homology by showing it's the same as cellular homology, or at least sketch how that works. I sort of alluded to it, but I didn't write anything down. That's just, if you wanted to, you could just, as I said, you could do that, and then you don't have to show d squared equals 0 or invariance under moves or anything. But I sort of prefer to see it as an independent theory which works all by itself and then happens to be equal to the ordinary homology. There's one other context in which you can reconstruct algebraic topology using differential stuff, and that's de Rham cohomology. You've seen that using differential forms. And that is the significant problem that it doesn't capture any torsion because everything's over R, right? And so you never have any elements of your cohomology which are non-trivial, but you multiply them, times 10 and then they're trivial, right? Because that doesn't happen over R. And so Morse homology is really the only way that I know of to capture torsion using differential topology, using a purely calculus-based homology, cohomology theory that actually that works over the integers rather than over the units, and therefore captures torsion. Before I do any of that, though, I want to just throw out a puzzle for you and think about this a little bit. And this is partly related to what Nick has been thinking about, but it's also definitely just stuff we've been doing in general. So I want to think about the function f. Well, we've talked about f sub t, which is a one-parameter family of functions in which a birth appears. And if I just have it as a function of one variable, I can say f sub t y, let's say, of x is equal to x cubed minus tx. And we've seen this before. If you just graph the plot of these functions, when t is negative, you just see a function like this. When t equals 0, you see this leveling off cubic phenomenon. And when t is greater than 0, you get 2 critical points. Okay, so this is the standard model for a birth of a pair of canceling critical points. If you wanted this to be in higher dimensions, remember you just call this x1, and then you throw in a sum of plus or minus xi squareds for the other x's. But what I want to do instead of thinking of that as a one-parameter family of functions of one variable is just think of it as a function of two variables, right? So I want to now talk about f, let's just call it f of xy, say. And so I'm going to change the role of x and y there. I'm going to say this is y cubed minus xy. Okay, just think of that as a function. This has, so let's see if this is a function from R2 to R. It has a critical point. Well, let's figure out what its critical point is. Well, we take df, and that's partial with respect to x, so minus y, comma partial with respect to y, so 3y squared minus x. And so that's equal to 0 precisely when x and y are both 0, because y's got to be 0, and that shows x equals 0, so the critical point is at 0, 0. Let's go ahead and see if that critical point is degenerate or not. Okay, let's compute the Hessian. So the Hessian, modulo, not remembering what rows and columns, which ones are rows and which ones are columns, The diagonals are the partials with respect to x with respect to x. So let's take, so this was partial with respect to x. So now I differentiate with respect to x again, I get a 0 there. This was with respect to y, I differentiate again with respect to y, and I get a 6y. And then the mixed partials should be equal, so I'll take this one. And partial that with respect to x, I get a -1 and a -1, right? And now I want to evaluate the Hessian at 0, 0. So at 0, 0, this is 0, 0. The Hessian of f is just 0, -1, -1, 0. That is a non-degenerate quadratic form. Okay, its determinant is non-zero. Let's figure out so that means that this should actually be a non-degenerate critical point. So let's figure out its index. Okay. You have to diagonalize this matrix in the quadratic form way of diagonalizing, and I claim that when you do that, the index is going to be -1. This is going to have a how do you see this? You take the matrix. Well, first of all, you can change. So we're just thinking of this as a so 0. If I take the matrix 0, -1, -1, 0. When you're trying to diagonalize a quadratic form, you sort of have to do a row. You do a row operation. You've got to do the same column operation. Does that make sense? So if you add this row to that,
conjugate by transpose.
Huh? What's that?
You have to conjugate.
You have to conjugate by an elementary matrix and its transpose, which basically means you do a row operation and you simultaneously do the equivalent column operation, right? So we can, this is equivalent to, let's say add this to that, right? And I get a -2 up here, but then I also have to add, well, let's do it step by step, sort of. Then I also have to add this column there, so really I should go to, what am I doing, -1. But I just add this to there, but then I have to add that to there as well, so that's -2. Do you understand what I just did? Okay, and then we can go back down here, and so if I add this to -2, and just do it in, right, well, let's try to make this, what I want to do is, I can add minus a row. So let me add minus this row here, and well, we can just do it over the rationals as well. I want to get zeros off the diagonal, right? So we just do it over the reals, and so I can add -1/2 of that row to here, and I'll get a 0 here, and I'll get a 1/2 here, but then I also should add -1/2 there afterwards. Anyway, you can get something like that, okay? So the point is that you can diagonalize, so now this says index 1, okay, 1 negative. There are lots of other ways to do this, right? Finding eigenvalues and so on. Anyway, this says index 1, which means that this is, so what this means is that if you try to graph z equals f of b, z equals y cubed minus xy, that should have a saddle, right? And a non-degenerate saddle. Now this is kind of, let's actually draw this graph, right? So I'm going to draw, let's try to sketch this out. We're going to do, x is going to go to the right. No, yes. Y is going to come out of the board, z is going to go up. I guess I got my, not a right-handed coordinate system, but I want x to go. No, I want, z. That's what I want. But it's not a right-handed coordinate system, I don't care. Okay, so, actually, no, let me make y go into the board. Okay, so, I've got a surface which, when x is negative, is sort of going up like that. Right, because x is negative corresponds to t negative over there. When x is equal to 0, it levels off. And then when x is positive, it's going to do this, that's at the front of the board, right? Which is a little, let me try and draw without the axes now. Now you sort of, so if I sweep from left to right, I've got a cubic that's slowly developing this critical point and tilting up. So I'll draw it, the following way. I'll draw it. What I'm going to draw is the image of the critical points now. So the image of the critical points, something like this. This is the cubic we've already seen. And then if I look at something like here, draw some slices of code. The point is you can actually see this as an embedded surface inside 3. Something like that. Do you understand what this point is? So here's a surface in R3, and here's a critical point for the height function, the z coordinate, right? And can you see that this is a saddle? That's my puzzle, first of all. This is not your usual saddle, right? The usual way you draw a saddle is this, and this, and something. This.
So, I mean, I guess if someone asked me what a saddle was,
Yes.
I would say it's a hyperbolic plane.
Right.
Which would mean something about like the principal curvature as being different sign. At which point I would point to that matrix.
Yeah, exactly.
We're done.
Right.
But
Someone also asks you if if your kid asks you what a saddle is, you say, well, it's a surface like this, a surface like this, right? Okay, well, it's a thing you put on a horse, right? But it's this thing where it's the surface where you go down here and go up this way, right?
So it's a question like a change.
So what I'm really asking for is, in some sense, can you implement the Morse lemma in a nice way in the setting? So can you find a actual change of coordinates, a nice change of coordinates? So that this goes to minus x squared plus y squared. But even before that, can you actually see the two in this picture? Can you see the two, the ascending and descending manifolds for this critical point, for example? There should be one direction that goes down and another direction that goes up.
Yeah, they're like bent ones.
Yeah, so maybe, so the descending manifolds goes up,
And then it
this
turns
thing
left.
turns and goes down, right? So the ascending and descending manifolds go like that and like that, somehow, right? What about the level sets? Can you see that the level sets intersect? So if you were to draw a contour map for this thing, what would the level set right to the critical point look like? Just in the xy plane. It also, you should see two things crossing transversely, right? The way to see the level set is the actual, if you slice it right across here, and you look down at it, the middle sheet, you can see a straight line. And then these two outer sheets, you can see something like this. Because, so here in the middle, you've got 3 sheets, right? There's the front one, the middle one, and the back one. So when you intersect with the middle one, you get the straight line going straight across. You intersect with the front one and the back one, you get these 2 points that come together. So I just like this as a non-standard saddle that actually is a saddle. And how they say is there ought to be some way to sort of turn this around and look at it from just the right angle where it actually looks a lot more like this.
Explicitly?
Is that? Well, I'm interested in explicit, we sort of, now you've kind of, okay, one thing I would be interested in doing is actually seeing the actual gradient flow for this, say with the Euclidean metric, and then seeing what the image of the ascending descending manifolds are exactly as curves, for example. Computing explicitly, but even just, I just think it's a nice challenge to explicitly find the change of coordinates. You probably don't want to use the full general proof of the Morse lemma because that, well, maybe you implement it that way, but it would just be, I don't know, maybe just intuit somehow a way to change coordinates, some capital X, capital Y, so that this function is minus x squared plus y squared. Okay, so, one more comment on Morse homology before I do cohomology. So, remember, Morse homology, we have a Morse function. In order to get it, we need the function and the vector field. Okay? And out of that, we get we get a chain complex. Let's say C star of depends upon F and V. And then we showed that if I take, we showed that given, the best way to say it is given F sub t, V sub t, a generic one parameter family connecting F0, V0 to F1, V1, what we really want to show, what we show is there exists a, let me try to summarize this. There exists a discrete times, a discrete sequence of times, sort of t0, 0 is t0, less than t1, less than dot dot dot, less than tn, which is equal to 1, such that, so this is just the Morse theory or the surf theory, such that f sub t, t0, v0, f sub ti, v sub ti, and f sub ti plus 1, v sub ti plus 1 are related by one move. And the move is either a burn or a death or a finger move or a handle slide, right? And therefore, the chain complex C star of F sub ti, G sub ti, and C star of F sub ti plus 1, B sub ti plus 1 are related by, I'll call it an elementary chain homotopy equivalence. So this is where you either just add a pair of generators and the boundary of one is the other and that's it, or you just have a change of basis, right? And therefore, the conclusion is therefore C star of F0, V0, and C star of F1, V1 are chain homotopy. And therefore, what I can conclude from that is that what this particular one parameter family, F sub t, V sub t, that family gives an isomorphism. A particular isomorphism from the homology of the chain complex from V sub 0, F0, V0, to the homology for the chain complex F1, V1. Because that particular homotopy between the two Morse functions breaks down a particular sequence of elementary chain homotopy equivalences, which gives a particular sequence, therefore chain homotopy equivalences induce isomorphisms. There's an extra level at which, so this is sort of pretty nice. It's a particular isomorphism. One thing you might like to know, though, is that that's it's sort of the isomorphism between them. You want to know they're isomorphic, but you want to know they're sort of canonically isomorphic in some sense. And so, what's the right way to state that question? The next thing you'd really want to do is think about a homotopy between two homotopies, right? So, in other words, if I chose a different one parameter family, would I get the same isomorphism? And the answer is yes. And I'm not I'm gonna think about whether I want to try and give you proof of that.
Is that true on the chain level, or?
No, it's true on the I mean, you're gonna get, what you're gonna look at now is a sequence of equivalences, maps between, you know, it's gonna get, the diagrams are gonna get pretty bad, right? Because you've got elementary, you look at, you get one chain homotopy equivalence for a certain move. And then maybe that move becomes a different move or a sequence of moves, and you get some other chain homotopy equivalences, you're gonna get maps going down and over in some sense. And so what, you know, so what one should check that two homotopies, say f sub f sub t comma 0, v sub t 0, and f sub t1, v sub t1 equals the same isomorphism. And this is called naturality somehow. There's some general setting in which you do this. First you show that something induces isomorphisms, and then you show that the things that induce isomorphisms, if they're related by some isomorphisms at their level, then the isomorphisms they induce are isomorphic or something like that. There's a category theoretic way in which to state all this, which is there's functoriality and there's naturality, and there are two different issues in category theory. Then how we will do this by considering generic homotopies between homotopies. Homotopies. And f sub t comma s, right? And then to do that, you have to understand what happens in homotopies. Yes.
I guess a question, maybe you've addressed this before. Are any two Morse functions somehow homotopic?
That's a good point. So any two, if we're mapping to R, the reals, any two Morse functions are homotopic for a really dumb reason, which is that any two maps to R are homotopic to the constant map. Okay. Now that homotopy is very far from being a homotopy like this. So so what we're doing is we're saying everything's homotopic to the constant map, which is a really dumb homotopy. Now that's now we're going to appeal to a general fact, which I loosely did how to do this, to say that if you perturb any homotopy a little bit, it will eventually break up into this sequence of homotopy.
I guess if you're thinking Morse functions to the circle, it might be a little more complicated.
Exactly. Once you've got Morse functions to the circle, then you've got non-trivial obstructions to making homotopic. So then you have to say, you have to divide Morse functions to the circle up into homotopy classes and maps to the circle, which is, so at first level you understand the algebraic topology of homotopy classes and maps to the circle, and then you
So I guess it's sort of a silly question. I've never even thought about a Morse function going to anything other than R.
Yeah, I want to spend some time on circulating Morse theory.
Could you maybe if you had two functions that went into R and you couldn't really tell anything about them, if you changed your image to be like the circle or something, could you start to pick up? I'm thinking sort of like in terms of homology when you go from
right, there is
R
extra
to origin and
there's extra information you can pick up through manifolds, for example, from circulating Morse theory. Actually, stuff like the Alexander polynomial knot is actually related to this. The Alexander polynomial knot, I don't know if there's zillions of different ways to discuss it. One, there's some purely combinatorial ways, but another way that's very nice is to think about the complement of the knot and think about its universal abelian recovery, which means the complement of the knot has a very complicated fundamental group, but it's always got this Z inside the fundamental group, which is generated by a meridian to the knot. And so you take the universal the covering space corresponding to that subgroup of pi1, and that that can be visualized as cutting the complement along the cipher surface, and that opens up, and then you stack, Z copies of those. That's this covering space, which then has an action of that Z on it by translation. And you look at the homology of the covering space as a module over Z adjoining T. This is getting really complicated, but and then the Alexander polynomial, some sort of characteristic comes from some matrix that, anyway, there's a correspondence there. The T in the Alexander polynomial corresponds to that action of the fun number. This is nicely explained in Rolfson. So you can think about that homology of you can think about taking that infinite cover and mapping it down to R in such a way that you've got many parallel copies of the cipher surface. You want them each to be, one to map to 0, one to map to 1, one to map to 2, and then everything in between maps sort of on a Morse function from 0 to 1 and 1 to 2, and then you can wrap that back up into a map to the circle. And you can forget about the infinite cover altogether, and you can say, I'm interested in a circle value Morse function on the complement of the knot. So
So
map
yes.
from the complement of the knot to the circle, and then you can think about the Morse homology of that thing, and you can sort of cover the Alexander polynomial in some way there.
So if your cipher fiber, there's like can you sort of almost see the Morse function to the circle,
Yeah.
sort of as like where you are on?
You mean if you're a fibered knot? You mean?
Yeah.
Yeah. So if you're a good example, a very good example of a circle value Morse function is take any three manifold that fibers over the circle.
Right.
That fibration of the circle is a circle value Morse function with no critical points, which right away shows you that circle value Morse theory, even without any critical points, can be very subtle because you've got all the complication that exists in non-trivial bundles over the circle, which is some mud from a bundle over the circle you think of as integral across something, where the right hand is and just to the left hand and by some possibly highly non-trivial different and so one thing that comes, there's a paper by Hutchings and Lee about this. It relates that Empiricus about it, talks about circle value Morse theory over three manifolds and relates it to something called Reidemeister torsion. I'm not sure how far into it I want to get, but it relates Seiberg-Witten invariance of three manifolds to some classical torsion of some module that you get from this circle value Morse theory. But the interesting thing is, you get sort of this algebraic topology for this circle value Morse homology, and you then also have to think about closed orbits of the gradient vector field, because the point is you got orbits that go from an orbit from a critical point to a critical point, flow from a critical point to a critical point. First of all, it might go around many times before it lands at a critical point. So you have to count how many times it goes before it goes somewhere. But then also you may have orbits that just never hit critical points, go from a point back to themselves. And this paper has all this kind of interesting stuff. There's like a zeta function for the counting closed orbits and so on. So it's pretty deep. Anyways,
Is that paper kind of, with what we've done in this course, do you think that would be readable, or is it still?
well, I
really
think the
high?
gauge theory might be unreadable, but it might be possible to sort of just take it as a black box that you don't care about and try to understand the algebra. I mean, there's a lot of algebra behind this torsion that I haven't, that's just algebra. And I'm not sure if I'll be, I might like to try and understand some of that later on in this course. Anyway, I'll come back to circle diagrams. Okay. So, all right, so I'm not going to do this, but this is in some sense something one should do. And then you have to say there are things like, in how can a one parameter family of functions change? It can change by, they swallow, like you can see this. or the critical point does nothing, and that can become this, those sorts of things, right? So we have, there's a lot, sort of a lot of work to do with that in reality. However, the point of that, the point of bringing that up is that you would like to, one thing you might want to think about is if you just have a element of homology. So you have, let's say, suppose you just have, so a question that would be resolved by this is, given, F0, B0, and F1, B1, right? And then let's say a critical point P for F0, let's say, right? Then you'll have a homology class for P, which is an element of the homology of the chain complex for F0, B0. The equivalence class there. Well, it's supposing that a critical point P is such that boundary P is equal to 0. Not everything. Okay, so if it actually is something, then and then the question would be, this is sort of just a general question. How do you find the corresponding linear combination of critical points for F1, V1? Right. I mean, of course, I just did a single critical point. Maybe you take the sum of them, right? Maybe I should say P equals the sum of others. In the case of critical points, this is more general, right? How do you find the sum of, let's say, QIs? QIs, critical points for F1, V1, such that the homology class of the sum of QIs equals the homology class for but this equals really means under this natural isomorphism, right? Because really this is a homology class for coming from one chain complex, and this is a homology class coming from a different chain complex. And how do you actually go from one to the other? And this, I just throw this out as some sort of general thing that I don't think is really well understood. One way to do it is to explicitly find the one parameter, explicitly find the homotopy from F0, B0 to F1, B1. And so that's not always easy to do. If someone throws at you two different Haygood splittings of the 3-manifold, it's not always easy to figure out how to go from one to the other by stabilizations and Hamiltonians.
But you always can.
You can, but that's just an existence argument that it's hard to implement. And a particularly interesting example is the case where you replace FV with minus F minus E. And that's going to be the hard Poincare question. So let's now do Morse code. Well, okay, one last comment there. The point is, being able to say, you just write down equal sign and being blind about this. All of this blah 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 about naturality was to lead up to saying that would make sense. In other words, I could just write down equal sign once I know that any two homotopies from F0, V0 to F1, V1 would produce the same isomorphism. Therefore, there's a natural isomorphism. It's not just not lots of different ones. So Morse cohomology, very simple. It's a new chain complex, and you get a new chain complex, which is just the dual of the original chain complex. So C upper I of, I'm going to suppress the dependence on F and V now. C upper I is just equal to the dual of C lower I, which just means homomorphisms from C1 into Ci into C. So it's not the vector space dual, it's the group dual. Okay? And so that has a natural basis, which is, so you can also think of it as span by, so the group generated by P dual, P star, something, where P star, P stars are dual, you've got all the critical points, dual critical points. P star is a function from the set of critical points of P star of Q equals delta P. Right? In other words, P is a critical point. Q is a critical point of index I. Q is also a critical point of index I.
But isn't it really like P sub? Like there's a P, there's one of those functions for every critical.
Right, I've generated by the set, oh, I'm sorry.
P sub P.
Alright, okay. I didn't want to, I could have used the index, but I understand. It's a set of all. So just, all I'm saying is the standard thing, that you get dual basis, right? And then I have to define the corresponding boundary map. And define delta star, that is just delta, which goes from C upper I to C upper I plus 1, and that's just the adjoint of the boundary map delta of some these columns, we call it F, for example. That's going to be an element, if F is an element here, and then this is an element there, so I should have to say how do I evaluate it on some critical point of index I plus 1 now. And we do the F of the boundary. That's the other thing that we have. And then it's not hard to see that boundary squared equals 0. It implies delta squared equals 0, which means you can now take the homology of this chain complex, but anytime you have a chain complex in which the boundary map increases index, I mean, it's just it's arbitrary to call this index, up or down, but if you increase the index, you call it cohomology. Okay, so then H upper star is equal to the homology of H upper star. H upper I is equal to the kernel co-boundary map from Ci to Ci plus 1 modulo the image of the co-boundary map from Ci minus 1 to Ci. And what's surprising is that there's anything new at all in cohomology. The first time I saw it, you dualize everything and think, why should there be anything different? If you've seen algebraic topology, you know that there is other interesting structures. But I want to focus on a theorem that is typically pretty hard to prove in the normal simplicial homology. It takes a lot of work, but it's sort of blatantly obvious in the Morse homology. So this is Poincare duality. Oh, well, so Poincare duality, let me just state it since I read it. Poincare duality says there exists a natural isomorphism D for duality from H upper I of the manifold of X to H lower n minus I of X, where X is a ring. Okay? It's natural in the sense, one thing I haven't talked about is, there's lots of, it's natural in the sense that it commutes with maps induced by diffeomorphisms and so on, and maps, but let me just sort of state how this works. So what we want to do is, the claim is this isomorphism actually comes from a chain homotopy equivalence between the dual chain complex and the original chain complex, but the indices switch. Okay, so proof is constructing equivalence. It's actually going to be simple isomorphism, in fact. It's going to be as nice chain homotopy equivalence as you would want, which is going to go from the dual, so I'm going to write down C n, C upper n, let me write the boundary maps. So let me write C upper 0 goes to C upper 1, these are the co-boundary maps, C upper, typical intermediate term, C upper I minus 1, C upper I, C upper I plus 1, goes to goes to C n minus 1, C n. That's the co-boundary complex. And then when you construct a chain of equivalence, it's going to map this to C lower n, maps by the boundary map, C lower n minus 1, n minus I plus 1, C n minus I, C n minus I minus 1, C 0. But the trick is that this is for f of v, and this is not going to be the chain complex for f of v, it's the chain complex for minus f and minus v. So this here is for minus f minus v. And so that's why we had it. If you believe that such a chain homotopy equivalence exists, that means that the cohomology, there's an isomorphism from the cohomology coming from f of v to the homology coming from minus f and minus v. And then you need what we already did to show that the homology for minus f and minus v is isomorphic to the homology for f and v. So that's why, I'm sort of kind of obsessed with this question of how you turn Morse functions upside down by elementary handle slides and bursts and deaths, because to me, that's like the smooth realization of Poincare duality. Poincare duality is a very hard theorem to prove. Well, it's not hard, but it's got, it's got transfinite induction. Also, it's a mess. The proof is a big deal in simplicial homology. The proof is sort of, in some sense, all the subtlety of that proof is hidden in claims about generic one-parameter families existing and being generic and so on. So it's all pushed off into analysis. But how the actual sequence of handle slides and bursts and deaths that realize Poincare duality, is the sequence of bursts and deaths that turn f upside down. And
So is the statement in
the general statement only works for oriented manifolds.
So is it also? I guess I don't remember from
Yes.
this. Is it also true on the chain level?
Yeah.
Like this. This seems to be saying something.
This is saying, what I'm saying is, you can interpret this as saying there exists a chain complex giving this homology, which is actually isomorphic
right to the
chain complex here.
So is
in
that
simplicial homology, that may not be true, because remember, the problem with simplicial homology is it's infinitely generated. Simplicial chain complexes, not simplicial, singular chain complexes are infinitely generated. And then you take duals, and infinitely generated duals are complicated, right? And so that's where a lot of the complexity rests. If you do the simplicial, there is a analogous proof of this for simplicial homology and cohomology, where you've got a particular triangulation of the manifold, and there's a dual triangulation, where every vertex is at the center of the face and so on. And then in that case, you actually get a chain complex. The dual chain complex is isomorphic to the dual. So that's what this is analogous to. And so, well, we can finish this in 3 minutes because it's pretty easy. The point is that, first of all, the map is clear because so the map's on the map from C upper I to C lower n minus I, right? Well, this is just so a typical element here is some P star, and we're just going to map that to P, because if you're a critical point for F, you're a critical point for minus F. So this is as a critical point for minus F, and this is, dual to critical point for F. Okay, and the index is the important point. When you turn F upside down, ascending and descending switch, so index I becomes index minus F. That's it. And then we just have, so that's what the maps are, and then we just have to check that it commutes, right? Or, which another way to say it is we just have to check that these things count the same thing, right? So what is co-boundary of P star is, well, we want to figure out what that is. So how about we evaluate it on Q? Remember, this is P star of the boundary of Q. And all that's saying is how many flow lines are there. So now Q is index I plus 1, and P is index I, right? Boundary of Q counts flow lines from Q down to things of index I. P star of it will pick up, so that boundary of Q will be a linear combination of critical points of index I, with the coefficients coming being the number of flow lines from Q down to that critical point. P star just looks at the P component of it, right? So this is just simply the number of flow lines from Q down to P. That's all. And now, if we go over here for minus F and minus V, the boundary of P is the number of flow lines from P down to Q. Those are flow lines for minus V, right? But Q was above P, and we counted flow lines from Q down to P. Turn everything upside down, we're counting flow lines from P down to Q. Those are equal. Therefore, that just shows you that when you push everything down by these maps, this linear map turns into that linear map. Therefore, the diagrams commute, and we're done. So, quantum duality is just turn everything upside down. Okay.
Shortest proof of point duality I've ever seen.
Something I'm not going to do that you might just puzzle over is if you've done cohomology, is cup product. Cup product, you think about it, just think about what that, think over the weekend, what would cup product mean? We're going to take two things of different index and get something. And think about cup product works in cohomology but not in homology, and why is that?